Hi, so I'm Colin Rice. My actual RCOS project is BitHopper, but Professor Morthy asked me to give a talk, and this is all I really wanted to talk about. So I'm going to talk about this. It has no relation to RCOS, really. I think I wrote it over Christmas break a couple of years ago. So this is a distributed hash table, and it uses G-Event, and it's in Python, and apparently it works. I've never used it, but some guy at Cornell did and sent me an email and was very impressed. So I'm going to explain how it works. So everyone here has taken, who doesn't know what a hash table is? Or like a dictionary?
Don't be shy.
Sweet. So everyone knows what a hash table is, right? So you take a key and you hash it and you map it to a slot in the array, modulus the length of the array, and you do stuff in collisions, and there's linear probing jokes, and it's very, very fun. And so a distributed hash table, you can sort of claim it works the same way. You take some data and you hash it and you put it some peers in a network, and then there's a big cloud on Wikipedia and they don't explain it very well. So what actually ends up happening is that when you make a distributed hash table, right, every node that's in the hash table, every computer or instance of the program has an ID, and you just randomly generate it, and this causes guys with IDs that are like, one apart, like one guy's here, one guy's in Antarctica, but the Earth is small enough that it still works. And so every computer has an ID, and given that you have an ID of the data, you can sort of use some mapping to get to the ID of the computer. I guess the most important part of this is making sure the computers can get to each other. So a really naive method is that you just have one computer that sits there that's always on, and that's node 1 or whatever you want to call it, right? So then you generate a random number and you connect to node 1, and node 1 goes, well, I know the next node, which is 2, and so you go talk to 2 and 3, etc., until you find your spot in the linked list, which may be, between 7 and 12. And so you talk to 7, it goes, oh, the next one's 12, and you talk to 12, and you tell both of them, hey, I should be between you, and you have a linked list, and thus you can find any node from the starting node or from your current location in the linked list. Obviously, that is horrible performance. So there's a couple other methods. There's the Chord method. Chord is a distributed hash table written at MIT in the 90s, I think. So what they did is they have a linked list, right? And then they added these log n lookups. And they wrote some fancy math to figure out where these should be, but basically it's like you go halfway around the circle, then you go quarter of the way around the circle, then you go like eighth of the way around the circle, etc., right? And so that way you can prove that there's log n performance, because if you want to find this node, well, you look at this and you go, it's closest to that one, you talk to that one, and it knows this one's closest, and then you're there. And so you can do log n lookups of computers. And then what you do is when you want to store a node, or a key in this set of computers, basically, you just look up what computer has that ID, and it will return you the computer closest to that ID, and then you tell that computer to store the item. And when you want to get it later, you do the same lookup and talk to it. So it's log n storage. So what our DHT does is it's a little bit less elegant than Chord, mostly because I didn't find the Chord paper when I wrote it. So what it does is it just starts bugging computers for stuff that's a certain distance away, so like 2 to the 1 distance away, 2 to the 2, 2 to the 3, etc., out to like, I think 2 to 128. So at best case, they'll have 128 peers. And it connects to all of them, and it's not perfect because it uses IP address to do it, so if you're behind a NAT, it's going to get a little sketchy. Like, it should work out. I tested it, but if your router's flaky, it won't work. Basically, if BitTorrent doesn't work for you, this isn't going to work either. And if BitTorrent does work for you, it still might not work. So the peers give each other information on hosts they know about. You can send out like free messages to try and find a host, and it'll like send back people who are closest to it. There's a lot of sort of underlying network protocol that works. And that's basically what we do. It's not as elegant as Chord. So it's pretty simple to use. You just make a distributed hash table, and you can set items, and you can get them, and you can append them, and then you can make another distributed hash table. All the hash tables have to have a starting node ID, because otherwise you're forming 2 disjoint graphs, and you can pull off of them. If you play with it enough, you can break it in interesting ways. So that's basically what a hash table is, and that's my bad implementation of it. So I'm going to thank Sean O'Sullivan, Professor Morthy, and Peter Halliday, who's the only one I know who ever used this, who's at Cornell, who's apparently in their IT department, and I guess their IT department's pretty badass and like writes distributed hash table using software. And he tweeted me on Twitter, and like 40 people looked at my hash table, and it was impressive because most of them appeared to like it. So that's it. Any questions about this? You, Alex Cameron.
Does it do any sort of replication or anything like that?
It doesn't explicitly do replication. It accidentally does replication because it may store multiple items, and then when the nodes realize there's a better node for their data, they'll send the data, but they keep it in their own local database, just because other nodes might think the data is supposed to be stored there. Also, it does make an attempt upon shutdown to spew out all its data to another node to be restored. It's not perfect, but it's decently good. It will notice when other nodes have died and drop them from the table. It doesn't send out death messages, but since all the nodes should be noticing that it died, because there's sort of a ping going back and forth every couple seconds, it works okay. You actually can increase the replication. Like, I wrote it so that you could change how much you wanted your data replicated. I never exposed the API because I forgot about it, but it's in the underlying code. So it's like probably 30 minutes to get it added and then another 5 minutes to make sure you didn't break anything. And you had a question.
So you said that you have to phone everybody to get your result back?
No, what happens is that you'll say, hey, I want node 5 million, right? Well, it's actually hexadecimal. It uses an MD5 hash, it's been shortened. But, and so what'll happen is you'll bug a node and then it will talk to the node it knows that's closest and it will go off like that. And so you don't actually phone the resultant node. I don't think there's any caching of like which nodes it should route through. But you can also do sort of an alternate lookup where you try and find the node at that point and it will tell that node to call you. But that's not what's used for lookups. It just routes through a bunch of other people and the result comes back.
So but it's pretty fast, right? It's sort of using a pseudo-chord ideology to get there, just not as precisely memorized.
Yeah, I mean, it's a little bit, chord is a very good idea, but in reality, you don't have an even distribution all the way around the graph. And so I don't know how chord deals with that. I know in our case, we just like take the log of the ID distance and then chop it off so it's an integer and shove it into our database. So it's actually, I think, the same idea as chord, roughly.
Just not as like nice and geometric.
Yeah, chord like takes account to like how long your numbers wrap, and like the distance function takes account of like the drop off over the edge, and mine doesn't do all that. Any other questions? Okay, well, I'm done.